I'm delighted to introduce our next speaker, Vivienne C. Welcome, Vivienne.
So, hi everyone, I'm Vivienne C. I'm a faculty member in the ECS department at MIT, and I work on energy efficient computing. Today I'm really excited to share with you some of the research we're doing at the intersection of computing, robotics, and AI. So in particular, what we're trying to do in our group is move a lot of the compute that happens in the cloud out to the edge into the robot. And the reason why you might want to do this might be latency. So for example, if you need to interact with the real world, you might not be able to tolerate the time it takes to send the data to the cloud, process, and get it back. So processing in the robot is ideal. However, we have a very big challenge, primarily power consumption. Right? So in these robots, you're collecting, or for example, a self-driving car, you're collecting over 6 gigabytes of data every 30 seconds. And to crunch through that data, you're actually expending over 2,000 watts of power. Right? This is just for compute. Right? And so this generates a lot of wasted heat. You also might need to spend some effort on doing water cooling to keep the processing heat dissipation down. And so this is for self-driving car, but these challenges become more significant when we look at smaller or low-energy robotics. Right? So there's actually a wide range of robots out there that consume under a watt for actuation. Actually, many of these robots are designed by or invented by people here in the audience. So for example, you can have miniature aerial vehicles. Where is it? Miniature satellites, lighter than air vehicles, and even unmanned gliders. And so you can imagine in these particular cases, you really want to keep your compute also very low. But unfortunately, existing processors actually consume too much power, right? So for example, in these particular robots, you want to have a budget of under a watt, let's say, to match the actuation. But existing, even embedded processors are burning over an order of magnitude higher power. You also can't afford to have very large batteries on these particular devices because of the weight and size limitations of these particular small robots. Okay? So what can we do? So over the past decades, what we'd actually do is we just sit and wait for the device physicist people to basically come up with better transistors, right? Following Moore's law and Dennard scaling, Moore's law would give us faster, smaller transistors. Dennard scaling would give us more power-efficient transistors. But what you'll notice is over the past decade, this trend has really slowed down, right? And this is primarily due to some of the physical limits that we're hitting. And so as a result, just to give you an idea, over the, if you think of last year when we did benchmarking tests, the improvement was just 3% in terms of speed, right? So while over here, we used to basically double in speed every 18 months, now if you extrapolate from last year's results, it would take 20 years to double the speed. So we can't rely on having faster and more efficient transistors anymore. So what can we do to solve this problem? Because we still need a lot of compute power for autonomous navigation. Well, we need to turn to designing specialized hardware, new computers. So you need specialized hardwares that give you the improvement in terms of performance and energy that you need for autonomous navigation. And what does that mean? That means that we need to redesign the computers from the ground up for this particular application, in this case, autonomous navigation and AI. So when you're going to design a new computer, the first question you should ask yourself is, well, where does the power go? So we can target that. So what's been really interesting that it's actually not the computation itself that's consuming all that power, but it's actually the data delivery. How do you actually move the data to the compute elements that burns a lot of power? So if we take a look at this graph, we can see that, going back here. So you can see that, for example, in addition, at different bit widths and different precisions can consume, in the sub-picojoule in terms of power consumption, multipliers a little bit more. Reading from an SRAM, so an SRAM is a memory that you would have on the processor chip in a very small SRAM, where here we're talking about 8 kilobytes, is going to be higher than all the compute. And then as you grow the memory size, the energy consumption is going to go up. And then if you can't fit the memory on chip, right? So for example, if you need to do DRAM because you have gigabytes of data, you're talking about orders of magnitude increase in power consumption. So just keep in mind that this is in log scale. Okay, so the main takeaway here is that memory access and data movement is really what's dominating the power consumption. It's something that we really need to address if we want to reduce the overall energy consumption of the system. However, when we turn to autonomous navigation, we actually need to use a lot of data. right? So if we just think about the visual processing side of things, if you're trying to do semantic understanding, meaning that you want to understand the label or what each pixel is, does this pixel belong to the grass or the sky and so on. First of all, you might need high frame rates, because if you're traveling very quickly, you need to have updates of your sensors very quickly. You need higher resolutions. So if you want to see very far away, the object might be very small. So you need to support high resolution. And then let's say you want to be able to detect objects of different scales. The typical thing might be building a pyramid, for example, and this is going to expand your data 1 to 2 orders of magnitude on top of that, right? So if you had an image that was HD with 2 million pixels, now you're getting into the hundreds of millions of pixels, right, per frame. The second type of visual data processing that you might want to do is geometric understanding, and that might be to understand the location of each pixel and the orientation of each pixel. This often happens if you're trying to build a map. And as you can imagine, as you explore or navigate more, the size of the map is going to grow, right? So if you're going to do robust and long-term autonomous navigation in particular, you're going to have to be able to handle a lot of data, and we know that this is a challenge in terms of compute, or in terms of power consumption. OK, so let's take a look at the very first step of what you would do if you're doing autonomous navigation, which is to figure out where you actually are, right? So your location and your pose. A very common technique of doing that is through visual-inertial localization or odometry. What does that actually mean? It means that you take in a sequence of images, as well as some IMU data, so inertial measurement unit data, so your gyroscope or accelerometer, and you want to fuse the data and then estimate your pose in the 3D space. So for example, here you have a video of some camera on a drone itself, and then here we're estimating its 3D position in an open space. If you're navigating through an unknown environment, you also have to create a map of that environment, for example. All right, so we've looked at this problem, and so what we did in our group was we actually designed a custom hardware that we call Navion that can actually do the localization in under 25 milliwatts. Okay, and so this, I just want to first emphasize, so this is the chip itself, this is Navion. It's 4 millimeters by 5 millimeters. You can see that it's small enough to be smaller than a quarter. You can fit it on a nano drone. And it does all the processing that is necessary for visual-inertial odometry, right? So it has feature detection. So shown here's the feature detection, tracking, feature tracking, outlier elimination. There's RANSAC on this. We also do sparse stereo and undistortion rectification. It also does all the front-end processing for the IMU. So it does pre-integration of the accelerometer and gyroscope data. And then in the back end, it does an optimization of the pose graph to fuse these two sets of data. So you can see, so one of the questions that we often get is that, OK, you're operating at very low power, so are you also operating at very low frame rates and speeds? Well, this particular chip can also operate at up to 171 frames per second from a camera input. And then the key frame rate is up to 90 frames per second. And this is all, again, at 24 milliwatts. So when you compare this to a mobile CPU or a desktop CPU, you're talking about 2 to 3 orders of magnitude reduction in energy and power consumption. Okay, so how do we actually do this? There should be no surprise. We really focus on reducing the data, right? So, well, there's 2 things. So for the first thing is we actually, as I mentioned, we want to integrate all of the processing on chip. Because for these small robots, you can't have multiple components. So you can see that this chip, as I mentioned before, contains multiple parts of it. The second thing, though, is as we mentioned, accessing data off-chip in the DRAM is extremely expensive, orders of magnitude more expensive than on-chip. So we want to integrate all of that data on-chip itself in local memories. And we've highlighted the local memories here. But we want to keep these memories also very small. So we apply various techniques. So for the frame information, we apply low-cost compression to reduce the size of these frames. And it has to be low cost because the cost of doing the compression should not exceed the benefit of shrinking down that memory. Then we also, on the back-end side, we look at exploiting sparsity in both the graph and the linear solver to, again, reduce the size of the memory as well as speed up the computation. Right? So again, by exploiting both the compression and the sparsity, we're able to shrink down the data, the memory required on this particular chip, to under a megabyte. Okay? Which is quite small. So, OK, so you know where you are now. Now, the next question is, can we understand our environment? And so this could mean something like depth estimation. So can we figure out the locations of the pixels relative to ourselves? Or as we talked about before, semantic segmentation. Can I figure out the label for each particular pixel? Now, if we think about the state-of-the-art techniques to do this, what is that going to be? Well, it's no surprise. It's going to be deep neural networks, right? So that's the obvious way of doing it these days. But the challenge is that neural nets require several hundreds of millions or billions of operations and weights to do this type of processing. Now, if we compare it to a type of processing that we're all familiar with, let's say video compression, and that happens on your phone all the time at a very low cost budget or low energy budget, this is going to be 2 to 3 orders of magnitude more complex than video compression. Right? So how are we going to cram all of this type of processing in the same power budget as we would have typically for embedded video compression? OK, so there are some things that are good about neural nets that we can actually leverage. So the first thing is, if you think about a neural net, all it's actually doing is multiplies and accumulates. And these multiplies and accumulates can all happen in parallel. So what that means is that high throughput is actually possible. We can operate very quickly. But what should be no surprise to you guys now is that the challenge is memory access. The challenge is how do you actually deliver the data to the multiply and accumulate engine itself. So here's the ALU, the arithmetic logic unit that's doing the multiply and accumulate. And so for every operation that you do here, you actually require 4 memory accesses, right? So you have to access the filter weight as an input, the image pixel, or if you're like more inner into the neural network, it would be the activation of the feature map. I'm just going to use image pixels to represent both. You would have the partial sums, and then you would need to update the partial sum and write it back out to memory. Okay, so that's a 4-to-1 ratio of access to compute. Then the next thing is the energy cost for each of these. So we know that reading, if you did the worst case, you read it from DRAM, for each of these memory accesses is going to be 2 orders of magnitude increase in energy per access compared to the computation itself. So if we take a very well-known neural net, just Alex as an example, although it takes 700 million multiplies and accumulates to compute, you would need 3 billion DRAM accesses to do that computation itself. And of course, if you go to more advanced neural nets like ResNet, this ratio would hold as well. Okay, so this is a significant challenge. But again, there's something nice about neural nets that we like, which is that there's opportunities for data reuse. Okay, so I'll walk through what this actually means is input data reuse is that the same pieces of data are going to be reused multiple times for different operations. So let's start here on the left-hand side. So basically, we have convolutional reuse. So if you're doing convolutional neural nets, which is the type of neural net you typically apply to visual data, you're performing convolutions. And what that means is that the pixels and then the weights same ones are going to be used, but just in different combinations. So you're reusing the input data a lot there. Another option of reuse is what we call image reuse. And when you apply multiple filters to the same input image, you can do that to generate multiple output channels. What does that mean? That means that each pixel in the input image can be reused multiple times across the filters. Right? And typically, you might have hundreds of filters, or even thousands of filters. And then finally, typically, you want to process more than one image at a given time. So any filter weight is going to be reused across multiple images. That's another reuse opportunity. So this is great. So how can we build hardware to exploit this? So in particular, what we want to do is we want to build hardware that exploits the reuse at very low-cost memory. What does that mean? That means that I want to build a memory, or put a memory, we'll call it a register file, that's very close to the compute, and has to be very small, typically on the order of under a kilobyte. And the reason for that is smaller memories consume less energy, and memories that are closer to the compute also consume less energy because you have to move it less. Okay? You can also allow each of these processing elements, so a processing element is an ALU plus a register file, to communicate with neighboring processing elements. And again, it's going to be cheaper to read it from your neighbor than to read it from DRAM. We'll have a shared global buffer memory, which is often on the order of 100 kilobytes to 500 kilobytes. And again, it's going to be cheaper to read it from global buffer than DRAM, and then DRAM is the most expensive. So just to give you guys an idea, if I need to do a multiply and accumulate, if that's 1x in terms of energy, reading from this very teeny tiny memory right by the memory is actually only 1x, it's the exact same amount of energy to read from this 1 kilobyte memory. If I read from my neighbor, it's 2x the energy. If I read from this global buffer, which is 100 k bytes, it's going to be 6x energy. And then if I read from DRAM, of course, that's the worst thing you can do. It would be 200x the energy. Okay? So in general, further and larger memories consume more power. And so now the challenge is as follows. You have this huge neural network with millions or billions of weights and feature activations. And you need to somehow store it in this very teeny tiny memory that can only store about 1,000 elements. right? So what you need to do is you take this large neural net, you break it up into smaller components, and then you process each of the smaller components. But now the question is, what is the order by which I process these smaller components, right? And this is what we call the data flow. So the order that I process these small components is the one that gives me the most data reuse. Okay, so that would be what we would call an energy-efficient data flow. There's a huge design space to search for that. And we did search for that, and so we built this chip called Iris, shown here, which does exploit this very efficient data reuse system. So in fact, if you look at the amount of reuse that you have, so if we're doing all the reads from this very teeny tiny memory in the processing elements and its neighbors, we're actually reducing the amount of reads from this expensive global buffer by over 2 orders of magnitude, so over 100x. And then the amount of reads from the DRAM by over 1400x, so over 3 orders of magnitude reduction of the reads from these two very expensive memories. So most of the memory and data access happens very locally, and it's much cheaper. Okay, and so all in all, we can run deep neural nets at under 1/3 of a watt. So this chip is shown here. This is a diphoto. This is 4 millimeters by 4 millimeters. So this is even smaller than that Navion chip we saw before that was smaller than 1/4. Okay, and when we compare it to a mobile GPU, we get an order of magnitude reduction in terms of energy efficiency. I should mention that this is the first version of Iris. We have another one that we just recently completed and gives us another order of magnitude reduction plus some additional flexibility. Okay, so that's neural nets. So now we know where we are. We can understand our surroundings. Now the next question is, where should we go next, right? How do you make that decision? And that really depends on what your task or your mission is. So let's say you want to do robot exploration. Basically, what you want to do is you want to explore an unknown environment, and you want to decide to go to the locations where you can get the most new information about the environment itself. One way of doing this is computing the Shannon mutual information to do this, but this is known to be extremely computationally complex. And so in the field, people have looked at approximate techniques of this or using heuristics that don't have provable guarantees. What we're going to show you today, and this is the first time we're discussing this here at Mars, is how we can actually build hardware to process Shannon's mutual information in a very efficient way, in a very high throughput way. Okay, so I'm going to talk about the key steps in terms of how you would use Shannon mutual information in the context of exploration. So the first thing you want to do is maybe select some candidate locations about where do I want to go potentially to get more information. Right? So where should I go to scan? And by scan, I mean scanning with a depth sensor, maybe a LiDAR. To decide which one of these are the candidates, I need to compute the Shannon mutual information at these potential candidate locations. So which of these locations would give me the most information, right? And then I would move to that particular location, and I would scan it. And then I would get an updated map based on this. So this is the occupancy map. It tells you where, in this particular grid, you might have some occupied locations. And then shown here is a small mini race car that's doing this exploration. You can see that it's computing the Shannon mutual information over here. So the bright spots indicate the locations that have the most information. So you should really go there if you want us to gather the most information about the map. And then you can see up here is the path plan to get there. And so you can see over here, there's going to start moving backwards to try and basically explore this particular location over here on the map. Okay, so this is great, sounds great, but what is the challenge here? It should be no surprise to you guys. Once again, the challenge is how do you deliver the data to the cores to do the processing for Shannon mutual information? So again, very, very similar to deep learning. Basically, as we're scanning with the beams for the LiDAR, all of these beams can actually be processed in parallel. So parallelism is not an issue at all. So each beam could be processed in parallel with a different core, and then you would just add up the different values, and you would get an estimate of the mutual information at that particular location. The challenge is how do we actually deliver the data from the memory that's storing the occupancy map to these different cores itself, right? In particular, one of the challenges that we face is that, once again, for the memories to be energy efficient, it can only afford to have 2 read ports. You can only read 2 items from it at a given time. If you want to read more than that, the memory is either going to be more expensive or very high cost. And the problem is we want to do all of this processing in parallel, let's say n cores. So how do you basically translate only 2 reads into keeping all of these different cores occupied and running at full speed so that you can compute the whole map very quickly? OK, so what we can do is you can actually build specialized memory architecture to do this. So if we look at the kind of read pattern for the different beams, shown here is basically the order in which they're reading. And so you can see the numbers basically indicate that these are the locations of the occupancy map that are being read in the same cycle, OK, being read in parallel. And you can see here that there's, we have multiple 3s, number 4s, so you can't be reading so much data from the same memory at the same time, as we mentioned, because of cost. So what we can actually do is you can take this large map and then break it up into smaller memories. Each of these memories will have 2 ports. And then you can access the data in parallel across these memories. But the question goes, how should I allocate my map to these different memory banks? So how should I do the mapping, or the allocation of the memory to the different maps? Mapping means something else. And so what we can do here is that we actually have a diagonal banking pattern. So what that means is that each of these different colors represents a different memory. Okay? And what you want to see is that you want to make sure that for any given color, only a given number only appears twice in that given memory bank. And that means that we can avoid conflicts, or read conflicts between the different cores, because again, we can only service 2 reads per memory at a given time. Okay, so by having this very specialized memory access pattern, we ensure that all of the cores can run at the same time, which means that we can achieve high throughput. And each of these small memories only have 2 ports, so that means that each of these small memories are very cheap and low energy. Okay, so what does that allow us to achieve? Well, then, as a result, we don't just have to compute the mutual information on a subset of positions, but we can actually compute it on the entire map. So for example, a map of 20 meters by 20 meters at 0.1 meter resolution in under a second. And so this is 2 orders of magnitude faster than a CPU and at 1/10 of the power. All right, so what are the key takeaways that I want you guys to get from this talk? So first of all, efficient computing is critical for advancing the progress of autonomous robots, particularly at small scale or low energy. And I believe that this is a critical step in making autonomy very ubiquitous. The second thing I want you to take away is that in order to meet the computing demands in terms of both the power consumption and the speed, we really need to design the computers from the ground up. And in particular, it's really important to focus on data movement. That's really what is limiting both the energy, or the speed, and the energy. And then finally, what's really exciting is that now that we're doing specialized hardware, we're opening up new opportunities for the co-design of both the algorithms and the hardware together. So a lot of the work that I presented today was a collaboration between myself, who's more on the computer architecture side, and Sertac Karaman, who is a roboticist in the Aero-Astro department at MIT. And we've been really working together in terms of what can I do as a hardware, in terms of the hardware, to enable more of the robotics applications in terms of an algorithm. And then on the flip side, if you're designing new algorithms and now you know that people are generating new hardware for you, how can you rethink all the algorithms that you do as a roboticist, right? You're no longer limited to a CPU or a GPU, but you now have a much more wide open design space, because you can think of new hardwares to support those algorithms. So it opens up new opportunities for innovations for the future of robotics. So thank you very much.